Hello! In this game dev video, we're going to take a look at the subject of arrays. We will cover arrays in general, Unreal's TArray, and multidimensional arrays. So let's get right down to it. First, some background. Generally speaking, in most languages, on the majority of platforms, the term array refers to a single block of contiguous, meaning altogether in one chunk, memory, which is used to store a number of things. The things that are stored determine how that memory is divided up. When you make a game with the Unreal Engine, it doesn't matter if you're using C++, blueprints, or a combination of both. The underlying principles are still the same. One of the simplest types of thing we might store in an array might be a byte of data. As computer memory itself is generally expressed as bytes of data, this one is pretty easy. If we have an array of 8 bytes, then what we have is a single block of 8 bytes used to store these things. Each element is simply each byte in the block of memory. If, however, we have a 4-byte integer, which might be called different things on different platforms, but here I'll just call it an int32, and we wanted a similar array of 8 of those things, then we would actually have 32 bytes of memory in our array, each element being the next 4-byte chunk. As just stated, an array is a single contiguous chunk of memory that stores a number of your things. But such memory allocations are finite. You can only really tell a computer that you have a specific number of things you want to store in an array and have it reserve a chunk of memory for you. If you asked it to store 10 things, for example, and you came back a bit later and decided you actually wanted to store 15 things, well, the computer can't, won't, or shouldn't let you just do that. For one thing, it might have already stored something else starting right after your original 10 things, so can't use the memory for your array. So, the size of arrays once you make them are basically fixed. This can be kind of annoying. Many tasks need something more flexible because they simply don't know at the time they're programmed how many elements they might require when they're actually running, and that number might need to change while the program is being used. So various languages and frameworks provide friendly features which get around this, which are usually referred to as dynamic arrays. Dynamic arrays allow the developer to declare and use an array which can be resized after it has been created, without the developer needing to be directly involved with the stuff going on behind the scenes that allows this magic to happen. That's a good thing in terms of just getting on with your work, but it's not so great if you don't realize how they are achieving this and what you might do to help them out, or at least understand some potential issues. Underneath the hood, dynamic arrays are just static arrays, which are being managed for you with some extra code. The underlying array is still a single block of contiguous memory. At least it ought to be. In the case of Unreal's TArray, when you declare one in C++, no actual memory is allocated. TArray has an init method, which will size the array to the number of elements you want and set all of those elements to a default value that you provide. At that point, memory has been allocated. TArray, like most dynamic array implementations, allows you to add new elements to the end of the array. Under the hood, the dynamic array reserves more space in memory than you actually asked for. That way, when you want to add a new item to the end of the array, it already has reserved space for it, and so it looks like your array was magically made bigger, generally without any performance issues. However, this little trick won't work forever. Dynamic arrays will only reserve a number of extra spaces, often a percentage of their initial size, and if you keep adding to the array, eventually these extra spaces will run out. When that happens, the dynamic array will go and reserve a new contiguous block of memory for an internal static array that is larger than the existing one, including more free extra spaces for adding more elements. Then it has to copy over all the stuff from its current internal static array to the new one. Obviously, the larger the array and the greater the size of the elements it has to copy, the longer that could take. In a game, that might be a noticeable performance problem if, for example, you were unaware that dynamic arrays worked in this manner, and you were adding many new items inside of a for loop, perhaps inside an aactors tick method, and your TArray was having to keep resizing itself. There are similar considerations when you use functions which remove elements from inside the array. As the array can't have holes in it, the items above the item which was deleted will now need to be moved into new positions. If you don't care about the actual order of the items in your array, this can be done fairly quickly by swapping the item to be deleted to the end of the array, exchanging it with whatever was there, and then deleting it. If you do care about the order of the items, and we often do, then the item needs to be deleted and all the remaining items must be shuffled down to fill the gap. Luckily, Epic has provided TArray with all the required methods to perform these operations for you, but again, you should understand the implications. There are other similar points regarding how you use TArray that you should be aware of, and these are talked about in the Unreal documentation. I know, documentation. It sounds boring, but TArray is an important and well-used construct in Unreal development, and it does have proper human-written documentation available, not like that auto-generated waste of space you get for many engine classes. It's well worth reading what Epic have to say about TArray, not just for performance reasons, but because they have implemented a whole host of useful functionality in there for finding and sorting, binary heaps, all sorts of things. There are methods which let you work with those extra space elements, or slack, that the TArray has, allowing you to know exactly how many it currently has, and to add extra space in one go. If, for example, you know you're about to add a number of new elements, and it makes sense to tell the array up front, so it can just resize itself the one time. And likewise, you may wish to reduce unwanted ones after deletions. If you'd like to know more about how TArray manages the memory behind the scenes for you, check out the documentation sections on Slack and raw memory. I've added a link in the description. So, multidimensional arrays. If you think of a regular array as a line of storage spaces, each with a number, its index, then a multidimensional array with 2 dimensions is more like a grid of storage spaces, with each space having 2 indices. You might call these x and y, or row and column, or just dimension 0 and dimension 1. Such things are common to many types of game: chessboards, tabletop-style battlefields, grid-based dungeon crawlers, isometric sprite games. All these things rely on some kind of 2D grid. Before we go on, though, let's just clarify some terminology so we're all on the same page. 2-dimensional, multi-dimensional arrays are always rectangular. That is to say, each row has the same number of columns and the other way around. There might be more or less columns than rows, but each row has the same number of columns and each column has the same number of rows. This is true for multi-dimensional arrays with any number of dimensions. You can visualize 2-dimensional arrays as rectangles, 3-dimensional ones as cuboids, 4 dimensions as... it hurts, make it stop. Nested arrays, sometimes called jagged arrays, are not the same thing. These are arrays that have elements which are themselves arrays. That might mean that each inner array contained in the outer array has a different number of elements, or no elements at all. You can achieve something similar in Unreal by first making a struct that contains a TArray U property, and then creating a TArray of those structs. Anyhow, jagged arrays are all well and good, but it's those 2-dimensional arrays I specifically want to focus on, because they have such application in games programming. TArray does not support a multi-dimensional declaration like a standard C++ array does, but that's not really as big an issue as it might seem. Just as a long paper strip of 100 squares can be rearranged into 10 strips of 10 squares to form one large square, we can do the same thing with TArray, using simple maths. If we want to make a chessboard, for example, which is an 8x8 grid, we know that 8 times 8 is 64. So we can simply declare a TArray and initialize it with 64 elements. Then set yourself up with a couple of helper functions. Given a row index and a column index, return the array index. And maybe you're interested in doing it the other way around. We can obviously take this further and create a class which wraps all this for us, allowing us to declare and use 2-dimensional arrays of any sizes we like. What follows is a very basic implementation of such a class, simply using an internal TArray for the actual storage. It considers the 2D array bounds fixed by the init function and does not support any kind of dynamic resizing. If that's something you need, you can implement functions for this yourself, which resize the underlying TArray also. You will obviously have to consider how you want to preserve the elements. With a 1-dimensional array, it's simple. You generally want new elements placed at the end. But with a 2-dimensional array, it might be a little more complex depending on your specific needs. Well, that's all well and good in C++, but how do Blueprint users who want to do something similar use this? Well, unfortunately, the short answer would be they can't. Trying to expose those templated C++ classes to blueprints is not trivial, to say the least. But don't despair, Blueprint friends. If you don't have access to any C++ mojo, you can simply make the equivalent of what the C++ code is doing for your own specific Blueprint classes. A Blueprint version can do pretty much everything the C++ version can. The only thing you need to bear in mind is that if you throw really big dimension sizes at it, it is probably going to perform slower than the C++ implementation would. Of course, it all boils down to how much processing you will actually do for each of these elements, and if you will need to iterate over all of them, doing lots of processing very often in your program. So let's take a look at a Blueprint version. In this example, we will consider that we have a Blueprint class called BP_thing, and that's what we want to store in a 2D array. What's in this thing Blueprint class isn't particularly important. It could be any class you like. The first thing I'll do is make a new Blueprint class to represent our 2D array. I'll call that one bp_2d thing array. Open that up and let's create the variables and functions that we need. First, some public functions. We want an init function to set up the array with the required dimensions and elements. GetElement2d will be how we ask the class to give us an element given our two-dimensional indices. SetElement2d is the complement. We will store a value into the array using two-dimension indices. We'll also have one private function, ArrayIndexFromDimensions. This will take our two-dimension indices and convert them into the single index that the internal array will use. This is private because it will never be used outside of the class itself. So then we need a few variables. They'll be marked as private. Internal array, this is the regular array of whatever type it is you want to store. In our case, it's an array of bp_thing. Size d1 and size d2. These integers will store how big each dimension has been set at, and then will be used to calculate the internal array index given the 2D indices. Array size is used to store the full size of the internal array once you initialize it. So what did the functions actually do? Well, init is what you call to set up each instance of the 2D array. It has two integer parameters that specify how big each of the two dimensions needs to be. It stores those values and multiplies them together to calculate the number of elements that the internal array will require. It then clears the internal array in case it had already been used and resizes it to the new size. GetElement2d has two integer parameters which determine the indices of the two dimensions you want to retrieve the element for. It calls our helper function that converts those 2D indices into the 1D index that internal array needs, and it uses it to get the value stored in that element, returning it to the caller. SetElement2d is very similar to the previous function, but it also has a value parameter, here simply called thing. This is the item we want to store in the element of the array, which we do with setArrayElement. ArrayIndexFromDimensions is our private helper function which simply maps our 2D indices to our 1D internal array. It attempts to check if the 1D index it calculates is within the bounds of the internal array, and if it is, it returns it. It writes a string to the log if something was wrong. And that's all there is to it, really. However you choose to go about it, it's quite simple to use one-dimensional arrays and map multi-dimensional indices onto them. That about covers the basics of arrays and using 2D arrays in Unreal. As always, I wish you much success with your own game projects. See you next time.